It's something most of us do every single day without giving it a second thought. But your car's drivetrain is an absolutely incredible piece of engineering. It's this hidden mechanical marvel that solves a fundamental physics problem every single time you take a turn. So let's dive in and break down how it all works. I mean, it seems like the simplest thing in the world, doesn't it? You turn the steering wheel, the car turns. But for the wheels that are actually putting power to the ground, well, turning a corner presents a surprisingly complex physics challenge. Okay, so here's the absolute heart of the problem. When your car makes a turn, the wheels on the outside of that curve have to travel a longer path than the wheels on the inside. The catch? They both have to finish that turn in the exact same amount of time. Now, if they were just connected by a solid axle, one wheel would be forced to slip and scrub against the pavement, or even worse, the immense stress would eventually just snap the axle. And this difference in distance, this is what we're going to call the cornering conundrum. It's the core puzzle that automotive engineers had to figure out more than a century ago. The solution is it's brilliant, and we can actually build it in our heads step by step. So first, just imagine splitting the axle clean in two. Okay, that solves the different speeds problem, but now, how do we get power to both wheels? Step two, you could try adding a simple bar to drive both halves, but that just locks them back together again, and we're back to square one. So the genius solution is step three. You replace that solid bar with a special set of gears. They're called spider gears. They can rotate, letting one wheel speed up while the other one slows down. And that amazing little device is called an open differential. It's this elegant, purely mechanical solution that lets the outer wheels spin faster than the inner wheel in a turn, all while continuously sending power to both. Problem solved, right? Well, almost. Which brings us to a really critical question. What happens when you're not on perfectly grippy pavement? What if one of your drive wheels hits a patch of ice or gets stuck in some mud or gravel while the other one is on solid ground? And this right here is the open differential's one major flaw, its Achilles heel. See, it's designed to send power to whichever wheel is easier to turn. On a slippery surface, the path of least resistance is the wheel with zero traction. So the differential does its job and sends all the engine's power to that one wheel, which just spins and spins, completely helpless, while the wheel that actually has grip gets nothing, and your car goes absolutely nowhere. So to solve that traction problem, engineers came up with all-wheel drive, which brings us to our next section, power to all four wheels. But as you might guess, this introduces a whole new layer of complexity. Because the second you add all-wheel drive, you run smack into the exact same issue we started with. When you're turning, the front wheels trace a wider arc than the rear wheels. That means the front axle actually needs to spin faster than the rear axle. If you just lock them together, the front and rear axles are forced to literally fight each other. This creates what's called drivetrain binding. It feels awful, causes jerky handling, and puts a massive amount of stress on all the components. So what's the solution? Yep, you guessed it, another differential. This one is called the center differential. It sits right there between the front and rear axles and does the exact same job as the first one. It allows the front and rear to spin at different speeds, which prevents that binding and makes sure you get smooth power to all four corners. But here's where it gets really interesting. Not all center differentials are created equal. This is where we dive into the great AWD debate, where different engineering philosophies are competing to strike that perfect balance between traction and control. The debate really boils down to two core approaches. On one side, you've got mechanical purity. These are systems that rely on the elegant, unthinking laws of physics. And on the other side, you have electronic precision, which uses a whole suite of sensors and computers to intelligently manage power. So let's look at the two big players here. On the mechanical side, you have systems like the torsion differential. They're permanent, they're always on, they use these incredibly clever worm gears that inherently and instantly divert power to the axle that has more grip. Then, on the electronic side, you have systems like Huldex. These are on demand. They usually just drive two wheels to save fuel and then use a computer-controlled clutch to engage the other two wheels the very instant that any slip is detected. Here's a perfect example of a mechanical system. Audi's crown gear differential. It's kind of like an evolution of that torsion idea. There are no electronics, no sensors telling it what to do. The very moment one axle starts to lose grip, the forces acting on these gears mechanically, just through physics, cause them to send the torque to the other axle. It's instantaneous because it's governed by physics, not computer code. And now for the electronic side. You've got systems like Mitsubishi's active center differential, or ACD. I mean, it's a completely different world. It's got a hydraulic unit, a multi-plate clutch, and a control module that is constantly reading data, from wheel speed sensors, the steering angle, how hard you're on the throttle. It's actively deciding millisecond by millisecond exactly how much power to send to the front and the rear.
Okay, so we've got these two competing philosophies, mechanical versus electronic. But why does any of this actually matter to you as a driver? Let's connect all this tech back to the real world.
Well, if that center differential starts to fail, you are definitely going to feel it. The most common symptom is this awful jerking or bucking feeling when you make a tight turn, like in a parking lot. It literally feels like the car is fighting itself. And that's that drivetrain binding up because the front and rear axles can no longer spin at their own speeds. You might also notice a shudder coming from the middle of the car or even see uneven tire wear.
So at the end of the day, each design comes with its own clear set of trade-offs. Mechanical systems, they feel incredibly planted and predictable, but because they're always engaged, they use more fuel. On the plus side, they're extremely reliable. Electronic systems are way more fuel efficient since they only kick in when needed, but they can sometimes feel a little reactive, and, well, with more parts like pumps and sensors, there's just more stuff that can potentially fail down the line.
And this quote really just hits the nail on the head. It sums up the core dilemma perfectly. There is no single best system. Performance drivers, they often love the pure, predictable feel of a mechanical system like a Torsen. But for a daily driver, the fuel efficiency you get from an electronic system like Haldex is a huge advantage. It all comes down to the engineering priorities for that specific car.
So that leaves us with one final thought to chew on. As our cars become more and more computerized, and as we move towards electric vehicles, will the elegant simplicity of mechanical purity survive? Or does the future of all-wheel drive belong entirely to electronic precision? It's a really fascinating question about the very soul of the machines we drive.